Okay, so today's topic is solving exponential equations today. So we're really going to build off of what we learned last class. Here we go. So we're going to greatly expand on the concept of exponential functions today by looking at solving exponential equations. I'll tell you what an exponential equation is in just a second here. But just a heads up, there's going to be a lot of review today because before we're able to solve these types of functions, we need to be able to do some of the old things that we would have learned in previous years. So the whole plan for today is we're going to review exponential functions from last class by giving you kind of a challenging question. This one's going to expand a little bit off of what we learned yesterday, but the same general principles are still going to apply. We're going to do some exponent laws review. Exponent laws are something you learned back in Math 9 and then really went in depth with in Math 10C. We need to review that today. Then we're going to talk about solving exponential equations algebraically as well as solving exponential equations graphically. So make sure you have your graphing calculator handy because you're going to need it for that part. Here we go. So this is a quick review of yesterday. Here's like a word problem type question that really builds off what we did. Iodine 126 has a half-life of 13 days. Now, for those of you not familiar with the concept of half-life, what this means is that the process of radioactive decay, as it progresses, half of the amount of iodine 126 you started with will be left after 13 days. Things that are radioactive like this will decay in a very predictable fashion, or relatively predictable fashion. Really can't tell exactly which molecules will go first and so on, but it will decay in a certain pattern based on what the material is. In iodine 126, it takes 13 days for half of it to disappear, right? That's basically all you need to know. So write an exponential function that can be used to represent the decay of a 100-gram sample of iodine 126 over time. Let's break this down into the little bits that we had learned from before. So we had y is equal to a times b to the power of x. That's the very, very basic, bare bones, simple way of looking at an exponential function. Now there's other things you can add in here. We can do some certain stretches and translations and stuff on here, but that can be added in later using the ideas that we would have learned back at the beginning of this course. One thing I want to tell you for sure though, is the a value in here, right up in front, is what we call your starting value. So it's the amount of whatever you have that you're starting with. Well, in the question itself, it's telling us we're starting with a 100-gram sample. So we can say right off the bat that A is 100. B, on the other hand, is your growth or decay rate. In other words, it's what you're multiplying by every single time. Now, we know we have decay. The question literally says decay right in it. So we're decaying in this case. And remember that decay tells us that B is going to be somewhere between 0 and 1, right? Now, again, thinking of your B value as what you're multiplying by each time is really useful here because the whole concept of half-life tells you that after 13 days, your amount is being cut in half. Logically speaking, that tells us that our B value can just be 1/2. So 1/2 will be the B value. Now, in this question, the x value here is going to represent our time. So it's going to represent how many days have gone by, and the y value will represent how much iodine 126 that we have left. But here's a bit of a problem. If we threw this in as y equals 100 times 1/2 to the power of x, if you plugged in, let's say, x is 1 day, you would see that you're going 100 times 1/2 to the power of 1. So in other words, 100 times 1/2. So that would be saying after 1 day, you'd have 50 grams left over. That's obviously not the case. We want that to be happening after 13 days. So we have to kind of play around with this basic formula right here to make it work so that when we plug in 13, that's where we're just multiplying by 1/2. Let me think about it another way. We can say y is equal to 100 times 1/2 to the power of 1 if x was 13, right? If x was 13 days, we would have a 1 here because that would mean we're just doing 100 times 1/2. So how can we make this 1 when x is actually 13? Well, what we could actually do is we could say that it's y is equal to 100 times 1/2 to the power of x, but then divide it by 13. That way, if x was 13, we'd be doing 13 over 13, which is just 1. Another way of looking at this is since you have half of it left over after 13 days, imagine if you went another 13 days, so 26 days in total. If x was 26, we'd have 26 divided by 13, which is 2, so you'd be chopping it by 1/2 twice. right? And that's exactly how half-life works. So in other words, with half-life, after 13 days, you'd have 50 grams left over. And then after another 13 days, you would have half of 50 left over, so you'd have 25 left over. In other words, it would have been chopped into a quarter. That's how half-life works. So this right here is actually our formula for the half-life of a 100-gram sample of iodine-126. Now, back when you were in grade 9, we actually did questions that were pretty much exactly like this. They were questions where I always said, oh, you're doubling or you're tripling or you're quadrupling each time. And oftentimes we look at it like, oh, an ant colony doubles its population every 13 days. Well, back when you were in grade 9, I very much simplified this down for you. Now, of course, in grade 12, you have to know a bigger, more deep explanation of this. But in grade 9, I always said that your final amount is equal to your starting amount times by, are you doubling, tripling, etc., to the power of the number of times this was happening, right? Now, we didn't have a variable up here in the exponent back when we were in grade 9 math, of course. We weren't dealing with true exponential functions, but we were still dealing with an exponential pattern of some sort, right? So in other words, if you wanted to say the number of times this is happening after 26 days, well, if it's doing it every 13 days, then you'd say the number of times was 2. So you're really doing this operation in your head before you're even putting it there. Anyway, that's an aside. This box here is the one thing we need to know. For part B, though, it says how much iodine-126 will be left after 50 days. Okay, since we already have a formula, it's just a matter of throwing this in, so I'll do it real quick. Y is equal to 100 times 1/2 to the power of 50 over 13. Make sure that that exponent is put in brackets when you put it in your calculator. I've already solved this. I've got it written down here. Y is equal to 6.95 grams. That would be how much is left after 50 days because it's been chopped in half numerous times. Anyway, moving on. So, introduction to exponential equations. An exponential equation is an equation where the unknown variable is an exponent. So again, the fact it's an equation is important. It's some side equal to another side. So this is an example of an exponential equation. 3 to the power of 5x minus 1 equals 81 to the power of 3x. You will be asked to solve for x in this case. In other words, you'll be solved for what value or values of x will make this statement true. Maybe it's x is 1. Maybe it's x is 2. Who knows? There's something that's going to make that equal on both sides. Now, in previous units, we've solved for when x was the base of a power, like in polynomials. So we've solved when you have like something like x squared plus 3x plus 4 or something, right? We've solved those types of questions. This was usually done by factoring, right? So in other words, we would usually find a way of factoring this somehow. We had several different strategies, but we can't factor this. When you have an exponent in a numerator, you don't know how many times this would have to factor down. With this, you knew. It was like, oh, it's x squared. It's an x times an x. That's pretty clear. But this is 3 to the power of 5x minus 1. So in other words, whatever x is going to influence how many times we're multiplying 3 by itself. So factoring becomes kind of useless here. You have no idea how many times we're multiplying that base by. That's what I'm trying to get at. So yes, if you're wondering, if we wanted to solve this, we could solve it graphically. We could say this is y1, this is y2, and then we could see in our calculator where each side is going to intersect. And we'll do that by the end of today, but I want to show you how to do that algebraically first, because life isn't always that easy. We gotta know the real details here. So we're gonna need to build some background skills before we can do this. Because clearly looking at this right now, it's like, how on earth can you get that exponent down? Like there's no way, like guess and check, I guess, but there's no way of doing that with the current skills we have, or at least so we think. All right, let's have a look. So I want you to recall from earlier grades the exponent laws. The exponent laws were basically just rules that dealt with the operations involving powers. There were several of them. A lot of them are just intuitive now. We've dealt with them so much. One of the basic ones is the multiplication rule. So if you had like something to the power of x times by the same something to the power of y, so two different numbers as exponents, you can combine it as one to be a to the power of x plus y. So in other words, if you did something like 2 to the power of 4 times by 2 to the power of 5, well, that's going to be 2 to the power of 4 plus 5, which is 9, right? And again, that's because this is 2 times 2 times 2 times 2 times by 2 times 2 times 2 times 2 times 2, so there's 9 2s, okay? Bottom line. Anyway, we don't have to prove all these. This is stuff you learned back in grade 9 as well, and you really reinforce it in grade 10. One thing I do want to say, though, is I want to combine this negative exponent rule, because remember, when you have a negative exponent, you just take the reciprocal of it and make it a positive exponent. I want to combine this negative exponent rule with this rule right here, the power of a fraction rule. If you have a fraction like a over b to a negative x, we can combine these two rules in one because notice the x is just going to go on each piece of the fraction. And also this one where it takes the reciprocal, a over b to the power of negative x is going to become b over a to the power of positive x, or in other words, bx over ax. Okay, so make sure you know that one because we're going to use it literally in like 2 seconds here. And there it is. There it is. See it right there. There it is. It's there. I told you it was like 2 seconds. Anyway, so simplify the following. Using the exponent laws, answers must not contain negative exponents. Math hates negative exponents for some reason, so we don't want them. Anyway, let's simplify all these. Notice we have something taken to a power. Well, this is a power of a power, so this power is just going to apply to all pieces. If we go back, you can see that when there's a bunch of things multiplied together inside of it and all taken to a power, the power applies to all pieces. We got to deal with that. So anyway, negative 3 to the power of 3 is negative 3 times negative 3 times negative 3, which I believe is negative 27. X to the power of 3 is just that, x to the power of 3. And then y to the power of 3 to the power of 3, that's a power of a power, so we got to multiply our exponents, that's y to the power of 9. You would have really went crazy with this when you were in math 10. There was a whole unit on this stuff. It probably would have driven you up the wall, but that's the way it is. All right, this next one, 12b to the power of negative 1/2 over 3b. A couple things I would do here first. I would, honestly, I would actually bring the negative exponent down first. There's several ways you could deal with this, but I'll say it's 12 over 3b times b to the power of 1/2. So in other words, we can just add these two exponents. 1 plus 1/2 is 3 over 2. Also, 12 divided by 3, that can just disappear. That can make it 4 over, again, this is b to the power 1 plus 1/2, so that's b to the power of 3 over 2. And a fraction as an exponent is also kind of uncomfortable. Let me just check back to see. I think there was a rule there. Yes, there was right here. When you have a fractional exponent, it becomes a root, where the numerator becomes the power on the stuff inside the root, and the denominator becomes the type of root you have, or the index of the root, right? So in other words, this can become 4 over the square root of b to the power of 3. And that would be your answer. Now, really, I'm just kind of like chuckling at this right now because in math, we also hate having a square root in the denominator. But, you know, we're going to pretend we didn't see that. We're going to move on. All right, next one. Negative 3 is our exponent. I'm going to deal with that very first things first here. So I'm going to flip this whole thing first. It's going to be 5. Oh, dang. I was going to say we're good here. But no, there's a negative exponent inside of here too. Shoot. You know what? I'm not going to deal with this negative 3 first. I'm going to deal with this negative 2 first. Inside the brackets first always. So I'm going to make this negative 3x3 y squared, because really you're just moving it up because it's taking the reciprocal of this piece. And of course, 1 over y squared on the denominator can move up to just y squared on the top. If you're not sure about that, please contact me. It's just a very quick trick there. 5 is the only thing left on the denominator there now, all to the power of negative 3. Now we'll apply that negative exponent by flipping the stuff in here. The negative here I'm going to leave on the top, because remember, a negative 3 on the top, might as well put it on the 5 because it really doesn't matter. So it's negative 5 over 3x3 y squared to the power of positive 3. Now that positive 3 can attach to all of these other pieces. Negative 5 to the power of 3 is negative 125 over 3 to the power of 3 is 27. X to the power of 3 to the power of 3 is x to the power of 9. Y to the power of 2 to the power of 3 is y to the power of 6. Now, one thing I'm going to check real quick here, because I do have a sinking feeling that this might reduce. I want to look at the negative 125 over 27 in my calculator just to see if that fraction can simplify. Nope, it can't. So you know what? Forget this equal sign right here. This is as simple as that's going to get, and we're good to go on that one. All right, next thing we got to deal with here, of course, and believe me, again, the whole reason we're doing this is we're marching towards being able to solve an exponential equation. It might not seem like it right now, but we are, believe me. So using your exponent laws, particularly the power of a power rule, you can rewrite the base of the power to something smaller. This is going to be really useful in a second here, believe me. Change each of the following to the base indicated. So we want to make 9 to the power of 2x have a base of 3. Well, the only way to do this is to look at the base and say, can I actually reduce this so that it does have a base of 3? Well, 9 is 3 to the power of 2. That's the relationship between 9 and 3 right there, right? So in other words, instead of saying 9 to the power of 2x, I can say that's 3 to the power of 2 to the power of 2x. Now this ultimately has a base of 3, but we can go further than this. 3 to the power of 2 to the power of 2x, that's the power of a power, so just multiply those together. That's going to be 3 to the power of 4x. And that would work a little bit better. It's the same thing as this, just with a base of 3. Let's do another one. 8. This dot here is supposed to be a time symbol, but whatever. 8 times 16 to the power of x. We want to change it to a base of 2. Do the same thing we just did here. 8 can be written as 2 to the power of 3. Times by 16 can be written as 2 to the power of 4. And then the x right here just stays on the outside. So this becomes 2 to the power of 3 times 2 to the power of 4x. And since we are multiplying two powers with the same base, we can just add the exponents. And I like writing the x first, so I'm going to write this as 2 to the power of 4x plus 3. Because again, with addition, order does not matter, so I just put the x first. All right, next one. We want to change this to a base of 5. 125 is 5 cubed, so I'll make that 5 cubed to the power of 2 minus x. So again, this is a power of a power. These need to multiply, so this becomes 5 to the power of 3 times 2 is 6, minus 3 times x is 3x. And I'll leave it just like that. Even though x could come first, I'd have to write it as negative 3x plus 6, but whatever, who cares, right? This one, this is where things get real challenging. 1 over 512, 3x. We want to change this to a base of 2. Let's focus in just on the 512 first, okay? That's going to be my hint on this one. 512 is actually 2 to the power of 9, okay? If you didn't know that, you could just play around with it and find it until you get there. But I can start right off the bat by saying that this is 1 over 2 to the power of 9 to the power of 3x. Now I'll clean up that denominator a little bit more here. We'll say that's 1 over 2 to the power of 9 times 3x, which is 27x. That's not quite a base 2 yet, though. The only way we can get this to base 2 is if we somehow were able to take the reciprocal of that. If only there was something in an exponent that can make us take a reciprocal. It's almost like we could say it's 2 to the negative 27x. So in order to make this question actually work, we're going to have to break our rule here and say, you know what, we will keep a negative exponent, and that's fine. If we wanted to really have a base of 2 here, we'd have to use that negative exponent to make that happen. Next one, 16 over 81 to the power of x plus 5. We want to change it to a base of 2/3. This one's kind of convenient because actually you can probably see that 2 can turn into a 16 and 3 can turn into an 81. 2 to the power of 4 is 16, and then thank goodness 3 to the power of 4 is also 81, right? So we could say this is, instead of 16 over 81, we could say it's 2 over 3 to the power of 4, and then that whole thing to the power of x plus 5. Well then, of course, that 4 is going to have to multiply with that x plus 5, so this is going to be 2 over 3 to the power of 4x plus 4 times 5 is 20. And there is your answer. Now that might have seemed like we did nothing at all there, that we were just doing some math tricks and stuff, but there was a method behind my madness here. We are going to have to use this in order to solve exponential equations. So the skills we just reviewed are going to be critical for algebraically solving exponential equations. Here's how you can go about doing it. Use your exponent laws. First things first, use your exponent laws to change each side of the equation, the left side and the right side, to have the same base. Then step 2, ignore those bases altogether and just solve for your x. So in other words, just solve the exponents that are left, okay? Oh, I pulled a sneaky on you here. We totally just learned these skills and it's gonna help us solve it. And if you don't believe me, here's that question I posted on one of the first slides. 3 to the power of 5x minus 1 equals 81 to the power of 3x. We're going to solve this one first. This is going to be the first exponential equation we ever solved. Let's go about it. Okay, 3 is our base on this side. That's not a big deal. We can't make that any smaller. But 81 can be written as a power of 3. 81 is actually 3 to the power of 4. Let's change that. 3 to the power of 5x minus 1 equals, instead of 81, we'll write that as 3 to the power of 4 to the power of 3x. Now we'll clean up this right-hand side here, so I'll leave the left side alone. The right-hand side is going to become 3 to the power of 4 times 3x is 12x. So this is saying 3 to the power of 5x minus 1 equals 3 to the power of 12x. Well, logically, this can only happen if 5x minus 1 is the same thing as 12x. So let's write that out. 5x minus 1 equals 12x. Let's gather all our x's to one side. So I'm going to minus 5x from both sides. Negative 1 equals 12x minus 5x is 7x. And then we need to divide by 7. So the only way that this would work is if x was equal to negative 1/7. There's no way you would have ever guessed and checked that. You would have been throwing in whole numbers this whole time, and probably positive whole numbers this whole time. If you don't believe me that this works, plug this into your calculator, and you're actually going to see that no matter where you put the x, whether it's on the left side or the right side, it's going to spit out the same answer. Oh, freaky. Anyway, let's move on. Oh, if it's going to let me move on. There we go. Now it's letting me move on. All right, solve the following exponential equations. If you want to give these a try on your own, you're more than welcome to. You can just pause the video. But I'm going to go over them right now. 7 to the power of x minus 2 equals 343. My best guess would be 7 to the power of something is probably 343. And my guess would be 7 to the power of 3. Just checking in a calculator now, and I'm right, it is. So that means 7 to the power of x minus 2 equals 7 to the power of 3. Therefore, ignore your bases, and we can say x minus 2 is equal to 3. Add 2 on both sides, that means x is 5. That one wasn't too bad. Gave us a whole number at least. There you go. Next one, this one's a little beefier. 2 to the power of x minus 1 equals 128 to the power of x times 2 to the power of x. Well, let's get a common base here on both sides. I know there's 2 different exponents or 2 different powers going on right here. Don't worry about that though. If we can get it to have the same base, we're good to go. 128, I'm pretty sure, is 2 to the power of 7. Yes, it is. I just checked. So this is going to be 2 to the power of x minus 1 equals 2 to the power of 7 to the power of x times 2 to the power of x. Cleaning this up a little bit more is going to give us 2 to the power of x minus 1 equals 2 to the power of 7x times 2 to the power of x. Since you're multiplying these together, that means you can just add the exponents because they do have the same base. This means we have 2 to the power of x minus 1 equals 2 to the power of 7x plus 1x is 8x. We can now ignore the not the denominators. We can now ignore the bases of this now. This is going to give us x minus 1 equals 8x. Let's minus 1x from both sides. This gives us negative 1 equals 7x. This is familiar. Divide by 7 on both sides. X is negative 1 over 7. I don't know why that had the same very obscure answer, but hey, you know what? It worked, so it's all good. All right, here's a couple more examples. These ones are way more challenging. If you want to pause and give them a shot, if you're brave, go for it. Otherwise, I'm going to go over it. 27 to the power of x minus 2 equals 1 over 81 to the power of x plus 3. This one might not be so obvious, but if you can kind of think about what numbers could be, turned from a power into 27 as well as 81, then you can start piecing it together. And one answer, of course, is 3. 27 is 3 to the power of 3. And so we'll make that 3 to the power of 3 to the power of x minus 2. And this is going to equal 1 over 81 is 3 to the power of 4 to the power of x plus 3. Cleaning this up a little bit is going to give us 3 to the power of 3 times x minus 2 is 3x minus 6. This is going to equal 1 over, 4 times x plus 3 is 3 to the power of 4x plus 12. Now notice because this is like a reciprocal right here, we can flip this around and just put a negative on this. So we're going to have no choice but to do that. 3 to the power of x minus 6 equals 3 to the negative 4x minus 12. So negative 1 has to times this entire thing, negative 4x minus 12. Now they have the same base, so let's just ignore that. 3x minus 6 equals negative 4x minus 12. Add 4x on both sides. I'm just going to do it, not even right there, I'm going to do it way up here. There we go. Add 4x on both sides, we're going to get 7x. You know what, I'll add 6 on both sides just for good measure. So negative 12 plus 6 is negative 6. Divide by 7 on both sides, x is equal to negative 6 over 7. Cool. All right, next one. This one is insane. Holy smokes, I'm not even going to read it out. You can see exactly how much of a beast this is. But again, look for any pattern you can. This has a negative exponent. The negative exponent, maybe we should get rid of that first. Getting rid of it means we can write this as 216 over 125 to the power of positive x over 4 equals 6 over 5, 3x minus 3. If you didn't do that as a first step, it's not the end of the world, but I just like doing that because now I'm a little bit more comfortable. And there's another really big reason why I did this. 5 can turn into 125 by taking it to the power of 3. 6 can turn into 216 by also taking it to the power of 3. So we can write this as 6 over 5 to the power of 3 to the power of x over 4 equals 6 over 5 to the power of 3x minus 3. This 3 can just multiply with the x over 4, so this is going to give us 6 over 5 to the power of 3x over 4 equals 6 over 5 to the power of 3x minus 3. Now we can ignore our denominators here, so we can say, not denominators, I don't know why I keep saying that. You can ignore your bases now. 3x over 4 equals 3x minus 3. just times everything by 4 to get rid of that divide by 4 there. So 3x is equal to 12x minus 12. Let's move this 12 over and move the 3 over. So 12 equals minus 3 here is 9x. Divide by 9 on both sides, and you're going to get x is equal to 12 over 9, but we can actually simplify that down as well. X is therefore going to equal 4 over 3. Good, awesome. Let's see. All right, a couple more examples. Holy smokes, these are really, really rolling. I didn't think it was going to take this long. You know what? I might actually just abandon this here. These ones are a lot more advanced. If you're interested in solving these, please reach out to me and I'll show you. You can give these a shot if you want, but I'm going to move on because we have already hit like almost 26 minutes. All right, so solving graphically, this is the last thing we need to know. Just so you know, it isn't always possible to get the powers on each side of the equation to have the same base. Okay, it's not going to work all the time. This trick we've learned today is great for the ones that it works for, but it's not perfect. It won't work all the time. There's an algebraic method using a concept called logarithms that we're going to cover another day that will let you solve those ones, right? So you'll have to understand what a logarithm is in order to do that. We're not there yet, though. That's still like that's a Mr. Miyagi trick that we haven't quite learned yet. So in other words, that's coming. We're not going to learn it today. It's going to take a while. But instead, for now, we can solve graphically. Now, in the formula, y equals 100 times 1/2 to the power of x, x divided by 13. From the beginning of today, that was the half-life formula where x is the amount of time in days, and y is the amount of grams left over. Find the value of x when y is equal to 10. Okay, so we're given a y value, so 10 grams left over. We want to find the value of x. So really we're saying 10 equals all of this. To solve this graphically, put one of the pieces into y1 and the other piece into y2. And I've already done this for you. Hold on. Bam! Bet you didn't know I could do that. Holy smokes, got a graphing calculator on my computer. Let me go. So I've already actually plugged this in. I just haven't fixed my window yet. If I press on y equals, you can see I've got it in there. I'll just move the little blinker away. So 10 is my y1, and y2 is the rest of that stuff right there. Make sure you're using brackets quite appropriately so you're not messing anything up. If I were to press graph right now under a standard window, you're not going to see much. We want to change our window and we want to do it logically. Notice how my window here is already like just a standard window. Since this is a half-life thing, let's think about what our minimum x could be. Well, the minimum x would be technically 0. Now, I don't like using 0. I like using just something a little less than 0 to give myself a little wiggle room. So I'll actually make my x min -1. So -1 days. In other words, we're talking about like what it looked like yesterday. My x max, on the other hand, is going to be a little bit different. Think about it this way. 13 days cuts it in half. So you'd be at 50. Another 13 days, so at 26, it cuts it in half again. So you'd be at 25. Another 13 days later, that's 39 days, you're cutting 25 in half, so you're at 12.5. Another 13 days after that, you'd be at, let's see, 52 days, and 12.5 divided by 2 is about 6.25. Bottom line is, I think a good x max would probably be something around, let's say, 55, just for good measure. My x scale doesn't really matter, I'll just make it 5, just so there's a good scale with it. Now, y is a different story. Y is reflecting how much of your iodine 126 you have left. Again, there's no way we're going to go below 0 on here, so I'll make it like -1 is my minimum. As for my y maximum, however, this is where you can be a little bit creative, but remember on y1 was equal to 10. We have to have 10 well within this window, otherwise we're not going to see the intersection point. You don't have to make y max 100. Even though you started at 100, you don't have to make it that much. And as a matter of fact, I would recommend against doing that, because otherwise your window is going to be too stretched out. What I'm going to do is I'm going to set my y max to 30, because that's going to give me just enough room so I can see this. And then my y scale, how about I set it to 10, right? Doesn't really matter. Let's press graph. Hopefully this will work. There's your y1 and your decay function. There it is coming down. That's your decay function. Again, we're only seeing a small cross section of it, and we can clearly see the intersection point right here. To find your intersection, you got to press second and then trace. That does the calculator portion, right? And then go down to where it says intersect. And then, of course, it's asking for a first curve. Just press your arrows until you get as close to it as you can. I don't even know if this step is needed. I just do it at a good measure. That looks like it lines up. Press enter. Then it says your second curve, same thing. Just move it until it's close. I'd say about there. Good. And then a guess, get as close to it as you can. That looks fine. Enter. So there it is. Our intersection is when x is equal to 43.18. So in other words, after 43.185 days, that would be where you'd have only 10 grams left. Now, it didn't tell us in this question what to round it to. I guess the nearest hundredth would be fine. So I'll say 43.19. Let me write that down. So x, oops, change slides. X is equal to 43.19 days. So after that many days, you'd have only 10 grams left. Cool. All right, anyway, we're done. Sorry about another long lesson there, but this was a really important one. Page 364, questions 4 to 10. I want you guys to give that a try. As always, if you have any questions, please let me know.